by email. Please look out for it over the coming days.
Yep.
But for now, Marco, thank you very much for your presentation.
You're welcome. Bye at all.
Very good. Okay, so that's our first presentation, and I'm going to now introduce Peter Kalker. Peter, if you'd like to start sharing your slides. I'm really delighted to have Peter with us today. He's CEO of Chema Process Control. He gained his PhD in physics from the University of Bonn in 1983 and subsequently worked in R&D across a range of industry applications from lasers to measuring equipment. In 1996, he founded Chema, which was renamed Chema Process Control in 2018. The company works primarily in the cement industry, supplying advanced closed-loop control systems to customers in more than 60 countries. Those of you who attend cemtech webinars will be familiar with Chema now, but it's great to be able to welcome Peter here for the first time. And over to you, Peter, now.
Yeah, good morning, good day, good evening to all our audience. I would like to welcome you to our presentation here. I hope that, it is working now. I want to present you fairly new devices that we developed mainly during the last 2-3 years. It is called gas temp and gas temp flow. It's an instrument that is able to measure the temperature of hot gases and even their flow speed simply by means of acoustics. This principle of measurement is not completely new. Some of you might have heard about it. This is already used in the power industry for a long time, but there were always some obstacles for using this technology in the cement industry. And I will show you what we did in order to overcome these obstacles and make this device available now even for the cement industry. Let's go ahead. Where can we use it? The basic idea for using this device was mainly to install it somewhere around the heart of the cement plant, the kiln. So you can see where we think that you can use the acoustic device for measurement of hot gases, the temperatures, and also the flow speed or the volume flow. You see, we have lots of possibilities. Most of them we already have realized, and we even found out by some customers that you could use it also on, for example, mills, vertical roller mills, for example, as an additional opportunity. Let's go. How is it working? Maybe some of you know the speed of sound of any gas. I emphasize any gas is a function of its temperature. To be more precise, it is according to the square root of the absolute temperature of the gas. And this is true for every gas, from helium or hydrogen to ambient air or to some other gases that we may find inside of cement plants. And that's a universal function that can be found for every gas, but I should mention the exact parameters of the square root depend on the composition of the gas. So the speed of sound is different for helium and as for example for air. Nevertheless, usually we know the composition of the gas, especially we do know it in cement plants, and then we have an extremely precise and very fast method to measure the temperature of the gases. For example, what you see here is the calculated transition time of an acoustic signal that is passing the duct of a diameter of 5 meters. You see it? The red curve shows what is the transition time for an acoustic signal when it's passing this 5 meters as a function of the temperature. And you see, we start with around 15 milliseconds and we end up somewhere in the range of 6 milliseconds if we have a temperature around 1,500 degrees centigrade. So far so nice. What is the advantage? The point is, when the actual measurement method usually employs thermocouples, and measuring gas temperature by thermocouples basically is an indirect measurement, because what do? You put in the thermocouple into the gas and hope that it will come to thermal equilibrium with the gas, and after some time it may be that it shows you the temperature of the gas if it has come to the equilibrium. I think most of you know that typically in the cement plant we not only have gases, but also we have lots of dust in the gases, and the gases are flowing, and if you put in a pure thermocouple, it will not survive very long, typically only a few hours. So what is done currently, they are cladded by steel pipes or ceramic pipes, and this makes them extremely slow. That means what I said, putting the device into the gas, waiting until it comes to equilibrium with gas can take minutes or even a quarter of an hour, depending on the case. And what is even worse, such a device as a thermocouple is also susceptible to radiation, thermal radiation. If, for example, you have the thermocouple close to the flame, what you measure is not only the temperature of the gas, but also the radiation of the flame. So you always get a mixture, and you do not really know what is the temperature of your gas. And this is completely avoided when you are using acoustics, because this phenomenon that the speed of sound depends on the temperature only is affected by the gas's temperature, nothing else. And the nice thing, as you see, we can measure the temperature by travel transition time. The system is the system is extremely fast. It can measure the temperature within seconds. And also we do not have anything to be put into the gas stream, and so the system is very, very robust and not prone to dust. Here I show you how we are doing it in practice. It's very easy. We have a transmitter which is emitting a short, sharp acoustic pulse, and we wait until this pulse arrives at the receiver. Typically during installation we know the distance between between transmitter and receiver, and simply by dividing the distance by the transition time, then we have the average of the speed of sound through this path. And that's the other nice thing. You do not get the temperature measurement at some distinct point. You get the average of the gas through the complete path, which is a much better measure of the temperature of your gas than you would have from a point measurement. Here you see some real signals that we have measured, in this case in a downcomer duct, where we had temperatures of around, I think 400 degrees centigrade. The red curve shows the pulse that is transmitted by the transmitter, and the green curve is showing what arrives at the receiver. Just a short word towards the pulse. If you see at the time scale, you see the pulse duration is in the range of only a few hundred microseconds. We have developed a completely new pneumatic pulse generator, which is able to produce these short pulses at extremely high intensity. So we get a really loud knock, which is traveling through our duct and is received at the other side. And we determine transmission time and arrival time, as you can see here, at the zero crossing. And then we can determine the arrival time down to the microsecond range. And this leads to nice, precise temperature measurement. Here you see the measurement that we made at the downcomer over a time of roughly 20 hours. The upper trace is showing the raw signals without any filtering. Already this is pretty nice. As you can see, it's of course varying because this is a measurement through a live streaming gas, and this will swirl and have vortices in any case. Nevertheless, it's already a pretty nice signal. For cases of closed loop control, we can filter this by means of digital filters and can make this as a basis for a very efficient and even then pretty fast closed loop control in order to stabilize the gas flow and even the so-called enthalpy flow of the gas that is transported. Here you see another example. In this case, this was measurement of the secondary air at the outlet of a kiln. Top two traces show two thermocouples which were above the measurement of our acoustic device. You see red and yellow show pretty nice temperature of around 1100 degrees centigrade. I would like to point your view on this time here. You see something was happening at that point, and the temperature of the acoustic system rose pretty fast, and the thermocouples realized this only several minutes later. It was more than 5 minutes. By the way, you see that the temperature that is shown in the green trace differs from the temperature shown by the thermocouples. This is mainly due to the fact the two couples are much closer to the flame. And as I mentioned, you see not only the temperature of the gas, but also the temperature of the flame. And also we have shifted the green trace a little bit down in order to make it more clearly visible what is happening here. And you see the reaction for a closed loop control could have been made nearly 5 minutes earlier than you would do with the thermocouple devices. When we came up with our system for our first customers, we were asked whether or not it would be possible also to measure the gas flow, because what you really need to know in order to control a kiln and to optimize the complete energy flow, or the thermal energy flow, was could we measure the gas flow as well? And here physics helps us, because in the case of sound, the movement of the medium where it is moving also adds to the speed of the sound. That means I have an example here, in this case a downcomer, gas is coming down, and the acoustic signal which is going against the flow is slowed down, while the other way, the acoustic signal going with the flow is speeded up. And the nice thing is if we can determine the difference in the arrival time, then we have a measure also for the gas flow. And if we simply compute the average, which would be a virtual signal that was traveling perpendicular to the flow, we get the temperature as well. And we have set up such systems also, meanwhile. And here you see what is happening. You see, once again, here we have a real signal that was transmitted. And you see the blue signal is the one which was going with the flow, arrived earlier than the other signal, which was traveling against the flow. And we have time distance here in the range of 180 microsecond. And this corresponds roughly to a gas flow speed of 22 meters per second. And the average was around 7 milliseconds through a duct of 3.5 meters, and this corresponds roughly to a temperature of 400 degrees centigrade. So from one measurement we get two very important informations about our gas. I see I'm getting late, Thomas. I will speed up a little bit. So,
yes, yeah, if you can. Thank you.
Yes, simply wanted to show you that the transit time difference is also a function of the absolute temperature, but as we can measure the absolute temperature as well, we can always calculate the precise gas flow, and then we have two signals that can be used in order to optimize the kiln. What you see here is an example of an installation of such a gas tank flow, as we call it, in a downcomer. In this case, I think it was a Heidelberg cement plant in Ennigerloh in Germany. Here you see the transmitter, and we have two receivers at the other side. Here you see the cooling signal. Blue is the temperature, red is the normalized volume flow. It's simply calculated from the gas speed and times the area of the duct, and then you get the volume flow. Just to show you what can be achieved in this case, this system has a measurement range for temperature from -20 degrees for up to 600 degrees centigrade. And for the flow velocity from 2 meters per second for up to 100 meters per second. I think this is more a theoretical point. And we have a different version that can be used at higher temperature. In this case, the acoustic horns, which are transmitting and receiving, are made of ceramics. These operate from -20 to 1,500 degrees centigrade. And the flow range is from 2 meters per second for up to 70 meters per second. Some more examples. I will go through pretty fast in order to give Jan another opportunity for his presentation. Here we have, once again, another downcomer at a Heidelberg cement plant. What you see here is an installation at the kiln hood. In this case, we have measured the secondary air. This is a plant in Dotternhausen in Germany. Here you see the secondary air temperature as compared to a thermocouple. You see a shock blower was shooting, and our system could see this, while you would have completely missed this with the thermocouple. And we have another example which I would like to go through pretty fast now. Here we have installed 4 systems at various locations of the kiln, and they are currently all working. And here once again is tertiary air flow, where we have temperatures up to 1000 degrees centigrade. And you can see them here. Secondary air temperature is blue. Tertiary air temperature is green. Pretty nice parallel, as would be expected. Again, a bypass. This can also be used in order to feed closed loop control systems, which then can stabilize the kiln. And here I would like to stop, and thanks for your patience, and hand over to Jan.
Peter, thank you very much. That's a really fascinating presentation of how it seems very simple how the system works. And as you said, the speed of sound in any gas is a function of its temperature. And just from that, see how
the principle is extremely simple. It's becoming difficult as soon as you try to do it in reality.
Yeah, I'm sure, but it's good to understand it. It's really elegantly expressed. A few questions. I was just wondering, when you're installing these systems, how difficult is that? Do you do CFD modeling to work out where you're going to position the sensors, or is it quite flexible? How does that work?
It is relatively flexible, but one should be honest. It is always better if you find a position where we have a more or less laminar flow. Mm-hmm. It means if you can avoid installing it close to any bending in the gas tank, you will get more reliable results.
Right. Okay.
But in principle, due to the operation with a short pulse, it would even work if you have some vortices.
Okay. There's several questions. I'll try and just go through a couple of them. What is the maximum temperature range that can be measured, and what is the maximum dust or particle load acceptable for reasonably good measurement?
Yeah. Maximum temperature range, I said, is 1,500 degrees centigrade for the ceramic version. Mm-hmm. The maximum of dust is a really good question. I would not recommend measuring, for example, in high dust load and air as, for example, in the cyclone.
Okay.
But you see, we can even do it in a downcomer, and there is still some dust around, and this worked. And we have installed systems at tertiary air duct, and this works as well.
Yeah. Okay.
For pure temperature measurement, as you saw, we even used it at the secondary air. It's a challenge, but we managed to measure even there.
And which are the most common uses of this system? Where is it applied most commonly?
Downcomers.
Downcomers, yeah. Okay. I guess there's always the question of cost. Are you able to talk about the cost of the systems and installation?
Yeah, that depends a little bit on the installation environment. Typically, it's around 20,000 euros.
Mm-hmm. Okay.
For a downcomer system, and a little bit more for a high temperature system.
Fine. Okay. A couple of more questions in the Q&A, but otherwise that's a very interesting presentation. Thank you for coming on and sharing that with us, and hope to see you again in a future webinar or at Cemtech in Barcelona. Thank you, Peter.
Yeah, you're welcome.
Yeah. Okay. That's great. Okay, so we're more or less on track. Thanks, Jan, for patiently waiting your turn. If you like to share your slides now, Jan Foged is from CC Jensen in Denmark. He earned his BSc degree in engineering in 2000, after which he joined CC Jensen in technical sales. He's worked across Europe, including Netherlands, Denmark, and Ireland. Serving multiple industrial manufacturing sectors, including cement. Jan is a certified machinery lubrication analyst with extensive experience in training in relation to oil maintenance, including oil filtration technologies. And he's going to present to us about reducing oil and maintenance costs in your cement plant and the benefits, including to CO2 reduction due to oil savings. So over to you, Jan.
Thank you very much, Thomas. And I'll hopefully give you a good of information that you can bring home to your plants. Just to give you an idea why clean oil is important, and we're focusing on the emissions today and the savings, of course. About 50 to 80% of oil changes could actually be eliminated. And unfortunately, a lot of oils are seen as consumable, and people should really look at oil as an asset and how to maintain it. Also, of course, decrease downtime, and by saving, you can actually decrease downtime up to 75% and even reduce spare part consumption by 60%. All lovely savings that I hope you'll all want to achieve, and I'll try to give you an idea of how you can do that. A quick introduction about C.C. Jensen. We're a Danish company established in 1953. We are originally came from the marine engineer, or the marine side of it, with Maersk as the founder of the company was a marine engineer on a Maersk vessel. But over the last almost 70 years now, we work with every oil type, every system that you can possibly imagine. As you can see here, wind, marine, power, mining, cement, and industry is our five kind of separated segments, but we work with everything. C.C. Jensen is in close cooperation with Noria. Noria is a tribology training expert from America, Tulsa, Oklahoma. And we have experienced presenters in the company that does these training courses in relation to wear and tear, and of course, oil guidance, best practice, etc. If you want more information on that, you can have a look at these kind of websites. If you look at a cement factory actually has loads of oil systems. If you look from you look at the mobile equipment. Of course, diesel is the main area that you look at, because without diesel, those equipment don't run. So filtering diesel is important, but you have hydraulics, transmissions, gears on the mobile equipment then that you can look at. You can also go then into the crusher, where you start your plant. Your crusher is almost all oil lubricated. You have your conveyor belts. You go into your raw mill, which of course with the modern designs now, you have the hydraulic system, you have the roller loop system, plus you have the gearbox. Then you look at, of course, the kilns, the kiln bearings, the gearboxes that are there as well. You have the coal mill, similar to the raw mill, oil systems there. You have the clinker coolers, also oil systems there. You have, of course, the cement mill, and on top of that, you can actually look at the power plants and the transformers that is also oil-filled. So on a cement mill, you actually have absolutely loads of systems that you can look at. In real quick terms, during an operation of oil, oil is actually contaminated when it comes into your plant. New oil is not clean oil. But what happens over time, an oil is of course worn out, it's run, it's contaminated. And what happens with that is it builds up particles, water comes in, acidity, oxidation. And what it does, it reduces lifetime. It reduces lifetime on the oil, it reduces lifetime on the pump and the bearing, and it also decreases reliability and efficiency. 80% of oil-related system breakdowns are due to contaminated oil. Sorry. If you have equipment operating on optimum conditions, if you roughly give it a guess on how long a lifetime you will have on an oil pump, most of you might actually see less than 5,000 operating hours. If you're lucky, maybe between 5,000 to 15,000 hours. Most likely you don't have over 15,000 hours. So it is really hard to kind of say what you get at the moment. But if you do run on dirty oil, result in loads of cases are maximum 2,000 hours on a pump life, which of course is going to cause you an awful lot of problems and you break down. To give you an example here, and this is a cement mill bearing, trunnion bearing on on actually an Irish plant here, which is a customer of mine. We had a very contaminated system. The pump was only lasting 3 months and had to be changed, with cost, of course, stoppages. It cost a lot of money to replace the pump, simply because the oil was dirty. We put in our filter, which I'll explain a little bit later, and by cleaning the oil down to 2 to 3 times cleaner than new oil, this pump lifetime went from 3 months to over 6 years. So a life extension of over 20 times. And of course, you don't have to change the oil. Oil is perfectly clean. Again, most of the oil on cement factories are chemically perfectly good condition, but just normally contaminated. So a lot of oil changes is simply because of contamination, not because of the chemical condition of the oil. And to give you an idea of the emission savings on just this alone, and that's based on oil produced, you have an emission saving of 151,200, which is always, of course, great to show to your green books. But also, and probably where most people are looking at money, if you look at the lifetime and the cost of the money and the pump, you see down below, the savings over the 5 years was over $32,000. A lot of these cement factories are very challenging. The environment is really, really dirty. It's a rough environment. It's very hard to keep systems sealed. It's very hard to keep system clean. And a lot of times it's basically impossible to get a cleaning level, especially standard 4406 on these applications. So sometimes, as you can see some of the pictures, some of the mills, some of the environments, the dirt is out of control. So it's very, very difficult. That, of course, leads to short lifetime on components. And some of these sensors and measurements and equipment that are on these mills and equipment most likely won't work efficiently because they are really dirty and it's really difficult to maintain. Oil lifetime could be easily less than 10,000 hours, and a lot of oil changes and a lot of costs are being spent in relation to this. Unscheduled downtime, of course, never good. You want to run the plant when you have to produce your cement. You want to run it when you have to. You don't want to stop and have to do maintenance, and it's going to be very expensive. Normally, we say 3 times more expensive to do a unscheduled downtime than it is a planned maintenance. Plus, there's also the safety issues that when you have to urgently do maintenance, safety sometimes go out the window, and the risk of accidents can, of course, increase. So really another side that you can get with this. So the challenging is, of course, existing filters. Why are they not working? Are they not good enough? In most applications and most systems, there's always filters to protect your components, to do different things. Because of the environment and because the balance of contamination is very, very different here, it is very, very difficult. Plus, all these filters are what we call low dirt holding capacity. They're small filters, small elements that will take a small amount of dirt out, and they have to be frequently changed because of the amount of dirt. They're actually not able to deal with. And inefficient filters performances, of course, causes you all the problems. Water oxidations are not removed because these filters are not able to do this. It's what we call mesh filters. If you look at the contamination in an oil, if you look at a human hair, it's approximately 70 micron. If you look at the biggest particles that the human naked eye can see, it is 40 micron. And if you look at 1 micron, which is very, very small, it is very, very important. The most damaged particles, those are the small ones that cannot be seen with the naked eye. And to give you an idea of the lubrication film thickness, different systems, of course, have different equipment, different tolerances. If you have a gearbox, you have hydraulic cylinders, your roller loop, or your roller element. If you notice all these, they're very, very fine. Like the hydraulic cylinders can carry the most or the biggest particles, 5 to 50, but the rest are actually very, very small. And most filters, inline filters, are not able to remove those very small particles. And those small particles will come into the fine tolerances. If you have a gearbox, it'll come between the teeth. If you have a roller loop, all of a sudden the particle will be between the surface and the roller, the bearing. If you have a valve, it'll come in between the valves, etc., etc. They're very small and they get in everywhere. To give an idea again what it is that this the size of these actually happens. If you look at particle distribution in a used oil, if you normally have let's say a 5 micron inline filter, 5 micron is actually only able to remove 30% of the contamination. So 70% of the contamination is smaller than 5 micron. 90% of it is smaller than 10 micron. Oh, sorry, bigger than sorry, confused there. So 90% is smaller than 10 micron. So as you can see here, most of the particles in your oil system is very, very small, and you can't see it. A standard inline filter are often between 15 to 50 micron, and they have very short lifetime on the elements. Give you an idea of a picture of a rolling bearing here system. As you can see, 10 micron is not a problem over there when it's in between the big tolerances, but by the end of it comes over, comes in between the two metal surfaces, and all of a sudden it's crushed, it causes friction, it causes wear and tear, and all of a sudden you have damage on your surface and you have a damage on the roller bearing. So the small particles get trapped between the moving surfaces and they cause more wear and tear. It's very important, therefore, to look at the tolerances on these, and the film, as we talked about, is between 1 to 3 micron, which most filters does not remove. So how do you protect these? How do you protect your investment? How do you protect your components? Best practice in an oil system is, of course, remember to seal the oil system. So you need a good breather, a good inline filter, which is probably already built onto the machine. And the inline filter will protect your system from wear and tear in your pumps or wear and tear in other equipment that can come in and damage your system. Then, of course, an offline filter, and filter that is very fine. It does independent circulation on the tank system. It takes from the very bottom where all the dirt is located, and it just circulates on the tank, continuously running, and you prevent all the dirt from having to go into the system. And of course, the breather is very, very important, especially in the dusty environment. A 10 micron filter, a 10 micron inline filter, and a 3 micron offline filter is what we believe is, to say, the total protection. So you can have the smooth lubrication system that you need. To give you an idea of what the filters that we work with and that we supply, it's 100% natural cellulose fibers from a sustainable resource. There's no metal, there's no plastic, and there's no chemicals. Our filters remove between 1 to 5 kilos and up to 4 kilos per insert, and water is removed as well, and varnish, which has become a very big issue on so many systems nowadays. Varnish is the sticky stuff that is generated when the oil is cracking in the oil, or the oil is cracked because of heat, and it sticks to the surfaces and sticks to the components, bearings, and then you no longer have lubrication, good lubrication. It's a very big contaminant in the systems. And to give you an idea of, well, basically a filter has to remove as much contamination as possible for the price. So the price of the filter insert compared to the price of the amount that it is removing. And if you look at a normal inline filter or surface filter, as we say, in this case, cost of insert is about $50. Cost of the offline filter is $270. But the capacity, the dirt holding capacity in the inline filter is only 0.085, where the offline filter is 4 kilos. Because it doesn't have to deal with the flow, the pressure, it is separate. So the cost per kilo removed is 270 for an inline filter, where it's only 31 for an offline filter. So 1/10 of the price to remove the amount of dirt. To give you another example here is a cement mill bearing system, very contaminated. We reduced, the oil was cleaned out, and of course in about a month and a half the oil was still very clean and kept clean. So as you can see that the graphs there before filtration, an awful lot of particles, small particles, but you reduce it down to basically nothing, and your lifetime is so much longer on all your components, bearings, gearboxes, pumps, valves, whatever that you could have here. And emission savings just on this one alone was 432,000. So it's a simple kit to actually remove or reduce your emission savings just by maintaining your oil instead of changing your oil. To give an example of a mobile filter, if you know, a lot of people say we'll put a filter on for a period of time and then we'll take it off again. Here you can see the comparison between the blue one. The blue is continuously offline filtration. The yellow is a mobile filter, and you can see the peaks going up and down. So when the filter is on, it's removed the dirt, brings it down to a good level. The minute the filter is off, it goes up very high, very quickly again. And the red curve is basically showing you the amount of contamination continuously with no filter on. And you can see that's very, very high. So to give you another example, we had a gearbox, a coal mill here, gearbox, very contaminated oil, a lot of coal in it, and we put on an online particle counter, so you can basically online see now the cleaning level on the system. In 5 days, the ISO code, the cleaning level of the oil was reduced from 25, 25, 21 down to a 16, 15, 11. This alone will give you emission savings on this gearbox to 540,000, which of course is what there's focus on today. But what we also realized here was when the offline filter was turned off for about a day and a half, it actually came back up very, very quickly to a higher level. And it took 2 times longer. So it took 3 days to bring it back down to the level it was before the pump was, or the filter was turned off. And it only took a day and a half to get back up. So again, continuously maintenance and continuous filtration will give you the benefits of these maintenance or these oil lifetime. To give you an idea of return of investments, oil changes, of course, is big issue. You know, you want to minimize the oil changes because that's where you can get a lot of oil. But inline filters, of course, a big price investment, and of course the downtime, production. Let's face it, everybody wants to produce. That's where the cement plants are making money off. Cement has to be produced and sent out the doors. To give you 3 examples here, and I won't go into the details of it, but if you look at after 5 years without a filter, the cost is $472,000. The cost with the CJC filter on offline filter is $175,000, and the cost in annualized savings or accumulated saving is about $300,000, which is a pretty good return of investment. And then you have the risk of safety on all these that are reduced, and you can start to plan and maintain your plant instead of having to firefight. Another benefit, which is of course one of the things that is focused on today, is and if you do go in and you fit the filter and you maintain your oil instead of changing your oil, the emission equivalent of these things could be something like this: 44 passenger vehicles driven for a year, 32 homes electricity consumption for a year, and 100,000 kilos coal burned, and 21 trips around the world in a passenger car. Now, we all have to do our part, and I think by you maintaining your oil, this will be something that will benefit everybody. Again, annual savings just on the CO2 could be up to 13,000 kilos. Again, and I'll make it really quick here. I think I'm on time. So conclusion is, what will clean oil give you? Well, it can give you a lot less oil changes. It reduces the OPEX savings on that. environmental benefits of the oil. Of course, everybody wants to reduce the uses of oil. This is one way of doing it. You want to decrease your downtime, and you can do that by up to 75%. So simply by maintaining the system, keeping it running, making it reliable, you reduce one of the biggest expenses in the plant, you increase production, you minimize breakdowns, your safety will improve because you don't have to firefight and fix things with short notice, better maintenance planning, and you will reduce spare time consumption by 60%. Longer lifetime on mechanical spare parts, pumps, gears, valves, and it'll increase the reliability of your equipment. It's very simple, very easy, but it'll be something that both can save you an awful lot of money, but also on the environmentally footprint, the emission savings. This is one way of doing it. And that FLS is a customer of ours and have been for many years. We started years and years ago, about 30 years ago, on the cemtech gear. Now we're looking at, of course, the Mac gear and their other equipment. And little comment here from FLS, which most of you probably know, CJC filters are the best investment with shortest return of investment you'll ever meet. And I hope that you will see the same, and hopefully some of you have already seen that by using our equipment. And that will actually run me to the conclusion of my presentation. If any questions, please feel free to ask. Thomas, I'll give you the word.
Thank you very much, Jan. That was a really clear, very interesting presentation, and yeah, it's very evident that the benefits of proper maintenance in terms of lubrication are just just layer upon layer of savings in terms of downtime, in terms of your operation. It's clear that the offline filtration is really important. That seems to be something that makes a huge difference. And is that something that you see most plants have or don't have?
Yeah, it varies. Some loads of plants does have it because FLS has recommended it for probably over 30 years on and off, depending on personnel, unfortunately. But yes, we have seen an awful lot of offline filters out there. But a lot of the times it comes down to management support to the loop people or the loop stores. It's down to education, awareness of how to maintain it and how to usually use the best practice. And sometimes there's no support in management because, like I said, oil is seen as a consumption or consumable and not an asset. So a lot of investment and training and education is not put into this area of the plant, which is an awful shame because it could actually save an awful lot of hassle for the management and an awful lot of money. So sometimes somewhere we see a well-fitted plant, and sometimes we have plants that doesn't do anything. So it varies a lot.
And how do you work? Are you visiting plants that come to you looking to improve their maintenance, or do you normally get involved in training? Plants?
We do a bit of everything. A lot of plants, of course, come and look at. We like to save the oil. We want to reduce the oil usage, and we look at how that can be done. We look at oil analysis and we say, well, your oil is highly contaminated, but it's in chemically good condition. So we advise on what the process has to be done. But we also run training for plants or companies that would like to get their maintenance group together and give presentations and training on what can be done and how they can benefit from all of this. So we basically do all of it. All depends on the management on each plant, what they like to do.
Are you able to give a figure for the amount of lubrication oil that a typical, 1 million ton plant will use? I mean, you've probably thought about this, but it's probably very difficult to assess. But is there any kind of ballpark figure? And I guess what I'm moving towards trying to understand is how, when you try and calculate CO2 savings, in terms of CO2 savings, lubrication is not going to be the biggest part of a plant's CO2 emissions.
No.
But having said that, everything is looked at nowadays. If you look at, a ton of CO2, an emissions credit in Europe, I don't know what the price is today, is 75 euros or something.
Yeah.
Everything counts now.
Yeah.
So I don't know if you can talk a little bit around.
I can't. Yeah, I don't have the figures because it is very difficult, as you said, and it's very hard to determine these things because every country is different, every plant is different, and people do different things. But I give you an example. I had a smaller cement factory here in Ireland that decided to go down this route of fitting every stationary system, every oil system, because a 5 liter little gearbox on a conveyor belt could be very, very critical for the whole plant to run. So that 5 liter is just as important as the 6,000 liters on the raw mill. So they've decided to go down that road and basically fitted it all and looked at it all. And they ended up only having to change 5 liters of oil every year.
Yeah.
And 5 liters of oil, you go, okay, that's nothing. They actually ended up having, they needed to buy in waste oil to use for their chain up on their, on the inlet area. I can't remember the name now. But so it's very hard to determine. But the savings are definitely there because the less oil that is being changed, the less oil has to be reduced or produced. So the less it has to be transported and gotten rid of and all these things. All that will come with it. I can't tell you the figures, but we all have to do our part. And this is one way that it could help everybody in reducing those things. The green footprint, as you said, how does people improve, the usage of oil? Well, here's one way.
Yeah, and these plants are looking for 5% savings, 10% savings everywhere, and it's part of that picture. And the other thing is obviously the savings from avoiding any kind of closures or inefficient operation, which then just add to costs in themselves. So
absolutely, exactly. So a smooth running plant where you don't have to stop and you don't have to heat up the coal mill or the raw mill or the kiln for stoppages. Well, if this can make it reliable, I'm sure the savings are much more than what I've just shown here.
Sure. Okay. Well, thank you very much, Jan. And thanks to all our speakers for their presentations today. To CTP, Chemo Process Control, and CC Jensen, I think you'll all agree we've had 3 excellent presentations, really useful, good engagement from the audience, and pretty much on time as well. So thank you, speakers, for all your participation today. We will be sending out the slides in due course, and you should get those in your inbox in the next couple of days, and you can follow up on the presentations, contact the speakers, or keep those on file for reference. So thank you for joining cemtech. Don't forget to check our website, go and have a look at the magazine, subscribe, and you can be reading it in the next 5 minutes. It's all there up on cemnet.com. But that's all from us today. A big thank you, and I hope I'll see you all in a month for our next cemtech webinar, which will be in about 4 weeks' time. Okay, so thanks you, everyone.